So this is a video for mechanical science experiment 4. So tau here is your torsional rigidity, and it's equal to the shear modulus G multiplied by pi multiplied by the radius of the wire divided by 2 times the length of the wire. We've also been given this equation here for the period of oscillation. So that is equal to 2 pi square root of I over torsional rigidity. So that I is the moment of inertia. That's the resistance of the mass to rotation, basically. So I, the moment of inertia, is equal to half the mass multiplied by the radius squared. This radius is the radius of your cylinder. So you should have a plot like this with t squared on one side and, t squared on the y-axis and m on the x-axis. You're going to get a line with a gradient, and the gradient's going to be y equals bx plus c. The equation for the line is y equals bs plus c, but b is your gradient. So basically, we need the gradient to solve for the torsional rigidity and the shear modulus. So basically, what you need to do is rearrange your equations. So you start off with this equation for tau, and this equation for t, the period, this one for moment of inertia. If you square that period equation, you end up with this, okay? And then after that, you need to replace the I, moment of inertia, with its full equation. So instead of I, you say half mr squared, and you end up with something like this. And from there, you can do t squared divided by m is equal to gradient. So I'm just going to move over there. So you see gradient there is equal to t squared divided by m. This is basically a bit of differentiation. It's not that important, but for our use right now, we can say that the constant doesn't matter. So we end up with y equals bx. So that way we can do y divided by x is equal to b. So long and short of it is, you'll get to this point. Yeah, so the gradient of your line B is equal to 2 pi squared divided by 2 multiplied by r squared over tau. You can rearrange to get tau is equal to this, basically. So that's 2 pi in brackets squared multiplied by r squared, and that's divided by 2 times your gradient. And then you can rearrange to solve for the shear modulus. So for tau, we just rearranged this equation. For the shear modulus G, you need to remember that this is another equation we started off with. So you literally just, rearrange for G. So that's how we've gotten G. Okay, so the last part, which is slightly trickier, it says, what is the moment of inertia at during the unloaded state? So if you look at this graph, all of our data points, those dots, they're taken at values of m. So basically, we don't have a value for m is equal to 0. But if we follow the line, we see at m is equal to 0, the line crosses the y-axis here. And that point where it crosses the y-axis, we can use that point and say that's t squared when m is equal to 0. And that's literally when we have added no mass to the system. So t squared here, if you take that value and rearrange I using this equation. So if you're wondering where I got this equation from, look at it carefully, and you might realize it's basically this, once again rearranged in, you don't even have to rearrange it that much actually, just do t squared, and you'll end up with t squared is equal to 2 pi in brackets squared multiplied by I over tau, and you can just rearrange that, and you will end up with this. And basically you say, okay, oh, sorry, bear with me a sec. Sorry about that. So yeah, you have I here, the moment of inertia. That's what we're actually solving for. We want the moment of inertia at during the unloaded state. So we find t squared at m is equal to 0. So find when m is equal to 0. Find what t squared is, and basically plug it into this equation.